What if I told you that the very fabric of reality is held together by a cosmic puzzle so deep, even the brightest minds in physics can't fully crack it? We're talking about quantum gravity, the grand challenge of understanding how the universe's smallest particles dance with the force that shapes galaxies. Picture this: the laws that govern a single atom seem to completely disagree with the laws that keep planets in orbit. It's as if nature itself has written two rulebooks, and no one can figure out how they're supposed to fit together. This isn't just some abstract scientific debate, it's a mystery that could rewrite everything we know about space, time, and existence itself. For over a century, physicists have been chasing a theory that can bridge the gap between Einstein's general relativity, which paints gravity as the bending of space-time, and quantum mechanics, which describes the bizarre behavior of particles at the tiniest scales. Think of it like trying to merge two languages that don't share a single word. The result, a battleground of wild ideas, from hidden dimensions to universes made of vibrating strings, each one more mind-bending than the last. And yet, despite all this brilliance, quantum gravity remains the ultimate missing piece in our understanding of reality. Why? Because every time we get close, the universe throws us a curveball: black holes that vanish into nothingness, particles that teleport through space, or the unsettling possibility that time itself might be an illusion. But here's the thrilling part: these aren't just dead ends, they're clues, and today we're diving into the 30 most astonishing theories that could finally unite these cosmic rulebooks. Some will sound like science fiction loops of energy weaving the fabric of space, holographic universes where our 3D world is just a projection. Even the idea that reality is built from tiny bits of information like pixels on a cosmic screen. Others will challenge you to rethink what's possible, like gravity leaking into our world from another dimension. So if you've ever stared at the night sky and wondered how it all really works, you're in the right place. By the end of this journey, you won't just see the universe differently, you'll feel it, because this isn't just about equations or experiments. It's about uncovering the hidden blueprint of existence itself. One of the most daring attempts to solve the quantum gravity puzzle comes from a theory that reimagines space itself, not as a smooth, unbroken fabric, but as a shimmering web of tiny, indivisible loops. This is loop quantum gravity, where the very stage of the universe is stitched together by threads of energy so small they make atoms look like giants. The idea was born from a simple but radical question: what if space-time isn't continuous, like an endless sheet of paper, but more like a finely woven tapestry, with gaps so tiny we've never noticed them? At the heart of this theory are spin networks, intricate structures where each loop carries a quantum of area or volume, like pixels defining the resolution of reality. Picture a frothy sea of these loops, constantly vibrating and interlinking every twist and knot, shaping the geometry of the cosmos. It's a vision championed by physicists like Carlo Rovelli, who compare space-time to a chainmail armor, flexible, dynamic, but built from unbreakable links. This isn't just poetic imagery, it's math that rewrites Einstein's equations at the smallest scales, replacing the smooth curves of general relativity with a dancing lattice of energy. Where loop quantum gravity truly shocks classical physics is in its answer to the Big Bang. Instead of a fiery singularity where the laws of physics break down, this theory suggests a big bounce, a moment where the universe rebounded from a previous collapse like a cosmic trampoline. The loops resist being squeezed to nothingness, creating a quantum wall that prevents true infinity. Imagine the birth of our universe not as an explosion from nothing, but as a phoenix rising from the ashes of an earlier cosmos. Yet for all its elegance, this theory isn't without controversy. Some argue it struggles to explain how the chunky, granular space it describes smooths out into the vast, continuous universe we observe. Others point out it hasn't yet fully reconciled with quantum mechanics' probabilistic weirdness. But that's the beauty of the hunt. Every unanswered question is a thread pulling us deeper into the mystery. And if loop quantum gravity is right, we're not just observers of the universe. We're part of its fabric, woven into the same dancing net of loops that holds the stars together. If loop quantum gravity is correct, it doesn't just tweak our understanding of space-time, it obliterates some of the most terrifying ideas in physics. Take black holes, those cosmic traps where gravity becomes so strong that not even light can escape. In Einstein's universe, their hearts are singularities, points of infinite density where the laws of physics simply give up. But loop quantum gravity rips up that script. Here, spacetime's granular structure acts like a safety net, preventing matter from collapsing into an infinitely tiny dot. Instead, the crushing gravity triggers a quantum rebound, like a rubber band stretched to its limit. The result, a black hole, might not be a one-way ticket to oblivion but a gateway to something else entirely, a white hole spewing out everything it once swallowed in a fiery rebirth. It's as if the universe has built-in emergency brakes, saving itself from the paradox of infinity. This quantum bounce doesn't just rewrite black holes, it reimagines the birth of the cosmos. The Big Bang, long thought to be the ultimate beginning, could instead be a turning point in an endless cycle. Picture a universe that contracts to a tiny, but not infinitely small, not before springing back outward. No mysterious singularity, no nothingness before time, just an eternal rhythm of expansion and contraction. Some theories even suggest echoes of past universes might linger in the cosmic microwave background, like faint fingerprints left by a previous incarnation of reality. The implications are staggering. If time isn't linear but cyclical, then every ending could secretly be a new beginning. But how do we test such a radical idea? One clue might lie in the faint whispers of gravitational waves. If space-time is truly granular, these ripples in the cosmic fabric should carry subtle distortions, tiny hiccups betraying the pixelated structure beneath the smooth surface. Future detectors, like the proposed laser interferometer space antenna, could hunt for these anomalies. Another tantalizing possibility involves black hole mergers. If loop quantum gravity is right, the violent collisions we observe might leave behind signatures, not a silent singularity, but a ringing remnant vibrating with quantum energy. Of course, not every scientist is convinced. Critics argue that loop quantum gravity's math remains incomplete, especially when it comes to blending seamlessly with quantum mechanics' probabilistic quirks. And without experimental proof, it's easy to dismiss as a beautiful abstraction. Yet that's the thrill of theoretical physics. Theories aren't just answers, they're invitations to ask better questions. Whether loop quantum gravity ultimately triumphs or falters, it has already reshaped the conversation, forcing us to confront the possibility that space-time isn't a passive backdrop but a dynamic, living thing, woven from the same quantum threads as everything else. And if that's true, then every black hole, every galaxy, and even you are just patterns in the dance of loops. While loop quantum gravity reimagines space as a fabric of woven loops, another theory takes a radically different approach. One where the building blocks of reality aren't particles at all, but tiny, vibrating strings. This is string theory, a framework so ambitious it doesn't just seek to reconcile gravity with quantum mechanics. It aims to unify all the fundamental forces of nature under a single mathematical roof. Imagine if every particle, from electrons to photons, wasn't a point-like dot but an infinitesimally small string, vibrating at different frequencies like the strings of a cosmic guitar. Pluck one way and you get an electron, pluck another and suddenly it's a quark. In this symphony of vibrations, even gravity emerges not as a separate force, but as a harmony woven into the fabric of the universe itself. Where string theory truly bends the mind is in its demand for extra dimensions. Our everyday experience tells us the universe has 3 dimensions of space and 1 of time, but string theorists propose at least 6 more, curled up so tightly we'd never notice them. Picture a garden hose. From afar, it looks like a simple line, but up close, you see it's actually a cylinder with a hidden circular dimension. String theory suggests the cosmos might be like that on an unimaginably tiny scale, with these extra dimensions folded into intricate shapes called Calabi-Yau manifolds. These aren't just mathematical curiosities. They determine how strings vibrate, which in turn dictates the laws of physics we observe. One configuration might give us our universe with its particular constants. Another might produce a reality where gravity is weaker or light travels faster. So why has string theory dominated the quantum gravity conversation for decades? Because it's shockingly good at resolving contradictions. In Einstein's relativity, gravity is smooth geometry. In quantum mechanics, particles are probabilistic and jittery. Strings bridge the gap by turning point-like particles into extended objects, smearing out the violent quantum fluctuations that normally break the math. Even black holes, those paradox factories, fit neatly into the theory. They're entropy-matching predictions made by counting possible string states. It's as if the universe handed physicists a jigsaw puzzle, and string theory is the only box where all the pieces snap together without force. Yet for all its elegance, string theory has critics. Some argue its extra dimensions and nearly infinite possible configurations make it untestable, at least with current technology. Others point out that after half a century, it still hasn't produced a single definitive prediction we can verify in a lab. And then there's the sheer complexity equations so intricate they've been called. A piece of 21st century physics that fell into the 20th century by mistake. But its defenders counter that revolutionary ideas often outpace experiments. After all, Einstein's relativity was purely theoretical for years before eclipses and atomic clocks proved him right. Whether string theory ultimately holds the key to quantum gravity or not, it has irrevocably expanded our imagination. It challenges us to think beyond the visible, to consider that the universe might be richer, stranger, and more interconnected than we ever dreamed. And if it's correct, then every atom, every star, and every law of nature is just a note in a grand vibrational score, one we're only beginning to decipher. String theory was already bending minds with its tiny vibrating strings and hidden dimensions, but then came M-theory. A twist so profound it made even seasoned physicists pause. Imagine discovering that the guitar strings you've been studying are actually just one instrument in an entire cosmic orchestra. That's M-theory in a nutshell, not just an extension of string theory, but a revelation that what we thought were 5 distinct versions of it were actually different facets of a single, deeper framework. The M stands for mystery, magic, or even membrane because at its heart, this theory introduces an astonishing new player, 2-dimensional membranes or brains floating in an 11-dimensional universe. Here's where things get wild. M-theory suggests that our entire universe could be a 3-dimensional brain drifting in a higher dimensional space, like a sheet of paper suspended in a vast, unseen wind. Gravity, unlike other forces, might not be confined to our brain, leaking into other dimensions, which could explain why it feels so weak compared to electromagnetism or the nuclear forces. But the real game changer is the multiverse. If brains can stack like pages in a book, each one might harbor its own universe with different physical laws. Some could have stronger gravity, others might lack quarks, entirely endless variations on reality, each playing out in its own pocket of existence. This landscape of possible universes is both M-theory's greatest triumph and its most controversial flaw. On one hand, it elegantly explains why our universe seems so finely tuned for life. With countless variations statistically, some would inevitably have the right constants for stars, planets, and biology. But for critics, this is a cop-out, a way to dodge the question of why our laws exist by invoking infinite dice rolls. Nobel laureate David Gross famously called it giving up on science, while others argue it transforms physics into a speculative guessing game. The debate boils down to testability. How do you prove the existence of dimensions or universes we can't touch, see, or measure? Some hope lies in high-energy particle collisions. If extra dimensions exist, the Large Hadron Collider might someday produce particles that briefly disappear into them. Others hunt for gravitational anomalies or cosmic signatures of brane collisions in the early universe. But until then, M-theory remains a breathtaking hypothesis suspended between genius and conjecture. It challenges us to consider that reality might be vaster and stranger than we ever imagined, and not just a universe, but a multiverse where every physical law is possible, and we're just one accidental masterpiece in an infinite gallery. What if spacetime isn't smooth or loopy, but built from tiny, iridescent shards of geometry like a cosmic stained glass window where every piece is a perfect four-dimensional shape? That's the bold vision of causal dynamical triangulations, a theory that ditches the infinite continuity of Einstein's universe for something far more radical. Space and time chopped into finite, triangular building blocks, each one a microscopic chunk of reality. Picture a universe assembled from hyper-precise Lego bricks, where every tetrahedron connects only to its immediate neighbors, and the angles between them dictate how gravity emerges on cosmic scales. But there's a crucial twist. Unlike other discrete approaches, this one puts causality front and center, ensuring time always flows forward, never backward. No tangled timelines, no paradoxes, just a clean, mathematical lattice where cause and effect are baked into the fabric of existence itself. The magic of this approach lies in its simplicity. Instead of wrestling with infinite probabilities or hidden dimensions, physicists start with these tiny geometric units and let them self-assemble through computational simulations. Throw in the rule that time must progress consistently, no loops, no jumps, and something astonishing happens. At small scales, the simulation churns out a frothy quantum foam, chaotic and fluctuating. But zoom out and order emerges. The triangulations spontaneously smooth into the four-dimensional spacetime we recognize, complete with Einstein's equations governing gravity. It's as if the universe is a puzzle that solves itself, with causality acting as the guiding hand that forces chaos into cosmos. Where causal dynamical triangulations truly shines is in its ability to sidestep the pathologies that plague other quantum gravity models. By strictly enforcing causality, it avoids the infamous spacetime foam problem, a scenario where quantum fluctuations rip reality into unstable wormholes and voids. Instead, the theory predicts a stable, large-scale universe that looks remarkably like ours. Even more compelling are its simulations of the Big Bang. Unlike loop quantum gravities, bounce, or string theory's brains, this approach suggests the early universe might have undergone a spontaneous phase transition, a moment when disordered quantum geometry suddenly crystallized into the orderly spacetime we inhabit today. Think of water freezing into ice, but on a cosmic scale, a primordial shift that turned quantum randomness into the reliable stage of reality. Yet for all its elegance, the theory has skeptics. Some argue its reliance on a fixed time direction feels arbitrary in a quantum world where particles routinely ignore classical intuition. Others point out that while simulations work beautifully in simplified models, scaling them up to our complex universe remains computationally monstrous. But perhaps the most tantalizing critique is also the most poetic. If spacetime really is a mosaic of geometric shards, what glues them together? The answer might lie in a deeper principle, one that transforms these mathematical triangles from abstract tools into the literal atoms of existence. Until then, causal dynamical triangulation stands as a daring reminder that sometimes the simplest rules can generate the richest universes. What if the solution to quantum gravity isn't exotic strings, hidden dimensions, or pixelated spacetime, but a mathematical trick hiding in plain sight? That's the promise of asymptotic safety, a theory so subtle it doesn't rewrite the rules of the universe, it just nudges them toward an elegant loophole. At its core lies a deceptively simple idea. Gravity might become predictable, even at the quantum scale, if its strength fades away at ultra-high energies like two magnets losing their pull as they're thrust apart. Unlike other theories that reinvent reality, asymptotic safety suggests we've been missing a cosmic fine print clause in Einstein's equations all along, one that lets gravity play nice with quantum mechanics without tearing spacetime apart. The magic hinges on something physicists call renormalizability. In quantum field theory, this is the mathematical process that tames infinities, those pesky calculations that blow up when you zoom in too close to a particle. Electromagnetism and nuclear forces are renormalizable. Their equations stay finite no matter how deep you probe. Gravity, famously, is not, or at least that's been the dogma since the 1970s. Asymptotic safety flips the script by proposing gravity might achieve renormalizability through a clever balancing act. Imagine a river flowing toward a waterfall classically, it's doomed to plunge into chaos. But if the river could adjust its speed and angle just right, it might instead reach a stable whirlpool at the brink, neither falling nor retreating. That's the essence of asymptotic safety. Gravity's parameters could fine-tune themselves at extreme energies, reaching a fixed point where calculations no longer spiral into nonsense. This isn't just abstract number crunching. If true, the theory predicts testable quirks in how gravity behaves at tiny scales. Particle colliders might spot deviations in how energy and momentum scatter, subtle hints that spacetime isn't quite as smooth as it seems. Black holes could reveal surprises too. Their evaporation might leave behind traces of this high-energy balancing act, like faint burn marks in Hawking radiation. Even the early universe might bear fingerprints of asymptotic safety, with cosmic inflation unfolding slightly differently than standard models predict. Yet for all its promise, the theory faces fierce skepticism. Critics argue that proving gravity reaches this mystical fixed point requires solving equations so complex they make string theory look like toddler math. Others point out that even if the math holds, asymptotic safety lacks the visceral imagery of loops or brains. It's a theory built on arcane calculus, not evocative metaphors. But its defenders counter that elegance often hides in simplicity. After all, Einstein's relativity didn't need extra dimensions or vibrating strings, just a radical rethink of how space and time interweave. What makes asymptotic safety so compelling is its humility. It doesn't demand we accept 11 dimensions or invisible membranes, just that we consider gravity might be smarter than we thought, capable of ironing out its own wrinkles without rewriting physics from scratch. And in a field where grand theories often collapse under their own weight, that might be the most revolutionary idea of all. Eric Verland's theory of emergent gravity hits physics like a lightning bolt. What if gravity isn't a fundamental force at all, but a side effect of something far stranger? Imagine walking into a room where the chairs and tables seem to move on their own, only to realize it's actually the floor subtly tilting. That's the core idea here. Gravity might not be a cosmic rule written into the fabric of reality, but an illusion created by the way information organizes itself in the universe. Verland's starting point is entropy, the measure of disorder that thermodynamics tells us always increases over time. In the 1970s, physicist Jacob Bekenstein discovered black holes have entropy mind-bending because it suggested these cosmic vacuums weren't just swallowing matter, but also information. Fast forward to Verland, who took this a step further. If space itself has entropy, then gravity could be its way of rebalancing the cosmic books, like steam rising from hot soup as the system seeks equilibrium. This isn't just poetic speculation. Verland's math ties gravity directly to holography, a concept suggesting our three-dimensional universe might be a projection of information encoded on a two-dimensional surface. Think of a credit card hologram. Tilt it and flat stickers appear three-dimensional. In physics, this means every event inside a volume of space, from colliding galaxies to your morning coffee cooling, could be described by data on its boundary. Verland argues gravity emerges from the way this information gets shuffled, like the invisible hand of thermodynamics nudging reality toward disorder. It's as if the universe is a vast, buzzing hard drive, and gravity is the system's way of defragmenting itself. The implications are staggering. For one, it could explain dark matter not as an invisible particle, but as an artifact of how entropy gradients warp spacetime in galactic halos. Picture a boat drifting on a lake. The water isn't pulling it, but the boat moves because the lake's surface isn't flat. Similarly, galaxies might rotate faster at their edges not because of hidden mass, but because space's entropic structure creates extra curvature. Experiments like the LIGO gravitational wave detector might soon test this. If gravity behaves differently in low-entropy environments, Verland's theory could leave fingerprints in the ripples from neutron star mergers. Critics, though, aren't convinced. Some argue Verland's equations don't yet reproduce all of Einstein's predictions, like Mercury's orbit with perfect precision. Others question whether thermodynamics alone can explain why apples fall or planets orbit without invoking deeper mechanics. But even skeptics admit the theory's brilliance lies in its audacity. It dares to treat spacetime not as a stage, but as a process, one that's constantly recalculating itself like a cosmic spreadsheet. Whether emergent gravity ultimately holds up or not, it forces us to ask, what if the forces we take as fundamental are just the universe's way of keeping its receipts? And if that's true, then every tug of gravity isn't a law. It's a receipt stamped by the cosmos itself. Causal set theory takes a radically minimalist approach to the fabric of reality. What if spacetime isn't just pixelated, but built from something even more fundamental, pure cause and effect? Imagine the universe as a vast, growing network of events, where each point is connected only to those it directly influences, like a cosmic family tree woven from moments rather than matter. In this view, the smooth, curving spacetime of Einstein's relativity is just an illusion, a shadow cast by the underlying skeleton of causality itself. The theory's founder, physicist Raphael Sorkin, describes it as atoms of time, where reality isn't defined by distances or durations, but by the unbreakable chain of which event led to which. The elegance lies in its simplicity. A causal set is just a collection of points with a single rule. If point A affects point B, they're linked. No coordinates, no geometry, just a raw relational map of happens before and happens after. From this sparse structure, something miraculous emerges. When you zoom out, the tangled web of cause and effect connections starts to approximate the smooth spacetime we observe, like a pointillist painting resolving into a landscape when you step back. Even gravity in this picture isn't a force but a statistical tendency, a side effect of how these causal links accumulate on cosmic scales. It's as if the universe runs on logic, not physics, with every star and galaxy just a pattern in the grand flowchart of causality. But the theory's beauty is also its biggest hurdle: dynamics. How does this static network of causal links become the evolving, expanding universe we see? Unlike loop quantum gravity or string theory, which start with dynamic equations, causal sets struggle to explain change. How the now slides into the next without a hidden clock ticking in the background. Some propose quantum mechanics could provide the answer, with probabilities governing how new causal links form. Others suggest time itself might emerge from the set's growth, like a tree adding rings. Yet after decades, no consensus has crystallized. Despite these challenges, causal set theory captivates philosophers and physicists alike. It strips reality down to its barest bones, no extra dimensions, no vibrating strings, just the irreducible notion that what happens matters. And in a world where quantum gravity often feels like an equation arms race, that simplicity is revolutionary. Whether it ultimately succeeds or not, it forces us to ask, what if the universe isn't built from stuff, but from the invisible threads that connect one moment to the next? What if the key to quantum gravity isn't hidden in new particles or extra dimensions, but in rewriting the very language of geometry itself? Enter non-commutative geometry, a theory so radical it suggests that at the tiniest scales, space doesn't just get pixelated, it stops obeying the rules of classical math altogether. Imagine trying to multiply two numbers only to find that 3 times 5 doesn't equal 5 times 3. That's the bizarre world Elaine Kahn's work opens up, where coordinates stop being neat labels and instead become entities that refuse to commute, meaning their order suddenly matters. In this distorted landscape, the smooth, predictable space of Einstein's relativity gives way to a fuzzy, quantum realm where geometry itself hums with uncertainty. Kahn's insight was to borrow from quantum mechanics' playbook. Just as particles like electrons don't have definite positions until measured, non-commutative geometry proposes that space-time points lose their individuality at Planck-scale resolutions. Picture a chalkboard where the x and y axes aren't straight lines but shimmering, overlapping smudges. Draw a curve here, and its shape depends on whether you moved left then up or up then left. This isn't just abstract noodling, it's math that forces gravity and quantum mechanics to reconcile. When coordinates fail to commute, the equations describing spacetime gain a built-in fuzziness that naturally tames the infinities plaguing quantum gravity. Suddenly, black hole singularities soften, and the Big Bang's violent fireworks smooth into a quantum blur. Where the theory gets truly explosive is in its ties to particle physics. Kahn and collaborators discovered that the same non-commutative framework that warps spacetime also predicts the standard model's particle zoo, quarks, leptons, even the Higgs boson, as vibrations in this twisted geometric fabric. It's as if the universe handed physicists a Rosetta Stone, one side scribbled with the arcane symbols of quantum gravity, the other etched with the familiar particles colliding in our detectors. The symmetry between them isn't coincidence but a clue that matter and geometry might be two faces of the same coin. Yet challenges remain. Critics argue that while the math is elegant, it's unclear how the fuzzy Planck-scale geometry sharpens into the crisp spacetime we experience. Others point out that testing these ideas requires probing energies trillions of times beyond our current colliders. But Kahn's followers counter that subtle signatures might lurk in cosmic ray showers or quantum optics experiments, where extreme precision could reveal spacetime's hidden non-commutative whispers. Whether non-commutative geometry ultimately unifies physics or not, it reshapes how we think about reality's building blocks. It dares us to consider that the universe isn't just stranger than we imagine. It's stranger than we can imagine, written in a geometric language we're only beginning to decipher. And if it's right, then every star, every atom, and every law of nature might just be a note in a grand, non-commutative symphony, one where order depends on how you listen. While most quantum gravity theories treat space and time as inseparable partners, Peter Horava dared to ask, what if they aren't? His radical idea, Horava-Lifshitz gravity, slices through one of Einstein's sacred principles, Lorentz symmetry, the rule that physics should look the same to all observers, no matter their speed. Instead, this theory gives time a privileged status, treating it as fundamentally different from space. Think of it like a film strip. Space is the individual frames, but time is the projector's relentless forward march, dictating how those frames unfold. By breaking this symmetry, Horava's equations perform a magic trick. Gravity becomes renormalizable, finally taming the infinities that plague quantum gravity calculations. The secret lies in anisotropy, a fancy word meaning gravity behaves differently at different scales. At everyday energies, however, Lifshitz gravity mirrors Einstein's general relativity, with spacetime smoothly warping around stars and galaxies. But zoom into the quantum realm and the equations shift. Time dominates while space acquires a fractal-like structure that suppresses violent quantum fluctuations. It's as if the universe has built-in shock absorbers for the tiniest scales, preventing spacetime from tearing itself apart. This isn't just mathematical sleight of hand, it's a calculated trade-off. Sacrifice the elegant democracy of space and time, and in return, get a quantum theory of gravity that doesn't explode into nonsense. Where this theory truly shines is in its vision of the early universe. Without Lorentz symmetry, the Big Bang transforms from a singularity into a dramatic phase transition, an event where time's privileged role kicks in, crystallizing the primordial chaos into orderly spacetime. Picture supercooled water suddenly freezing, one moment liquid randomness, the next rigid ice. Horovà's equations suggest something similar happened in the cosmos's first instance, with gravity's anisotropy acting as the cosmic refrigerator. This could solve long-standing puzzles like why the universe appears so uniform. If time froze before space had a chance to develop wild variations, it would naturally iron out wrinkles, explaining the eerie smoothness we see in the cosmic microwave background. Yet for all its ambition, however, Lifshitz gravity has critics. Some argue that breaking Lorentz symmetry contradicts countless experiments confirming Einstein's framework. Others point out that the theory struggles to explain how time's special status emerges dynamically, rather than being baked in from the start. But recent work hints at possible resolutions like hidden mechanisms that restore Lorentz symmetry at low energies, masking the asymmetry in our everyday experience. The debate is far from settled, but that's what makes it thrilling. Whether Horovà's gamble ultimately succeeds or fails, it forces physicists to question their deepest assumptions, and in science, that's often the first step toward revolution. Roger Penrose saw spacetime not as a stage but as a dance, and his twistors are the choreographers. Unlike strings or loops, twistors don't exist in space, they define it, weaving the fabric of reality from pure mathematical relationships. Picture a beam of light traveling through the cosmos. In Einstein's world, you describe its path using coordinates, latitude, longitude, and time. But twistors flip this inside out. Instead of tracking where the light is, Penrose's framework captures its entire essence, direction, energy, even quantum spin, as a single, shimmering geometric object. It's as if the universe's GPS switched from mapping streets to encoding the purpose of every journey. What makes Twistor Theory so elegant is its economy. By treating spacetime events as secondary phenomena, shadows cast by deeper twistor interactions, it sidesteps the infinities that plague quantum gravity calculations. Imagine trying to solve a maze by lifting the entire puzzle into a higher dimension where the path becomes obvious. That's the power of Penrose's approach. Complex problems in four-dimensional spacetime often simplify into elegant equations in twistor space. Even black holes, those notorious paradox factories, take on a startling new form. Their chaotic interiors might translate into smooth, solvable geometries when viewed through the twistor lens, offering fresh hope for unifying quantum mechanics with gravity. Yet for all its beauty, Twistor Theory faces a glaring hurdle: tangibility. While strings vibrate and loops intertwine, twistors exist in an abstract mathematical realm that's notoriously hard to link to measurable physics. Critics argue it's like having a map so perfect, it no longer corresponds to any territory. The theory excels at reformulating known physics, rewriting Einstein's equations in dazzling new forms, but struggles to predict new phenomena testable in a lab. Even Penrose admits twistors may be too pure, a language so divorced from familiar reality that translating its insights back to concrete predictions feels like decoding hieroglyphs without a Rosetta Stone. Recent breakthroughs, however, hint at hidden bridges. Twistor-inspired methods have supercharged calculations in quantum field theory, helping physicists crack problems once deemed unsolvable. And some researchers speculate that twistors might underlie the holographic principle, the idea that our three-dimensional universe could be a projection of information stored on a two-dimensional surface. If true, then Penrose's abstract dance might be the key to unlocking spacetime's deepest secret, that all we see and feel is just a shadow of a richer, stranger reality. Whether twistors ultimately reign supreme or remain a beautiful abstraction, they've already reshaped how physicists think, proving sometimes the most radical ideas aren't about adding layers to reality but stripping them away. Supersymmetry arrived on the physics scene like a perfectly tuned orchestra. Each particle in the Standard Model was promised a hidden twin, a cosmic mirror image that could solve quantum gravity's roughest edges. The theory, affectionately dubbed SUSY, proposes that every fermion, the matter particles like electrons and quarks, has an untapped boson partner force carrying particles like photons and vice versa. Picture the universe as a grand ballroom where every dancer arrives with a shadow partner moving in perfect harmony. These superpartners wouldn't just be decorative, their extra quantum properties would cancel out the chaotic infinities plaguing gravity at tiny scales, like a mathematical bomb soothing spacetime's fractures. Supergravity takes this elegance even further. By weaving supersymmetry into the fabric of general relativity, it transforms gravity's equations into a shimmering tapestry where every thread is accounted for. Suddenly, the force that bends galaxies aligns seamlessly with the quantum jitter of particles, as if the universe finally found the Rosetta Stone to translate between its two rulebooks. Some versions even suggest gravity's quantum carrier, the hypothetical graviton, could have a superpartner, the gravitino, a particle so elusive it might only reveal itself in the aftermath of cosmic collisions or the birth of the universe itself. Yet for all its theoretical grace, supersymmetry faces a glaring problem. We've never seen these superpartners, despite decades of hunting, from the tunnels of the Large Hadron Collider to the depths of underground detectors. The promised twins remain missing. The equations once whispered that these particles should appear at energies we've already probed, yet the detectors stay silent. It's like throwing a party where half the guests never show, leaving physicists to wonder, did they get the address wrong, or is the universe playing a different game entirely? The lack of evidence has dimmed SUSY's star. Critics argue that continuously tweaking the theory to push superpartners into higher, untested energies risks making it unfalsifiable, a beautiful idea that can always retreat over the next horizon. Others point to alternative frameworks like string theory or loop quantum gravity, which don't hinge on undiscovered particles. But SUSY defenders counter that absence of proof isn't proof of absence. The LHC has only scratched the surface of possible energies, and future colliders or cosmic observations might yet spot a gravitino's ghostly trail in high-energy neutrino streams or anomalies in the cosmic microwave background. What makes supersymmetry so compelling, despite its struggles, is its audacious elegance. It doesn't just patch up quantum gravity. It reimagines the universe as a place of hidden symmetries, where every particle's existence hints at a deeper, more balanced cosmic order. Whether SUSY ultimately triumphs or fades into history, its legacy is secure. It taught physicists to listen for the universe's hidden harmonies, even when the music seems to stop. And sometimes, the most revolutionary ideas aren't the ones that win, but the ones that show us how much more there is to hear. Black holes aren't just cosmic vacuums, they're laboratories for the most extreme physics imaginable, and their secrets might hold the key to quantum gravity. Picture a black hole not as a static pit, but as a seething, dynamic entity that obeys laws eerily similar to thermodynamics. This connection, first uncovered by Jacob Bekenstein and later refined by Stephen Hawking, shattered the old notion that black holes were simple, one-way traps. Instead, they radiate, they have temperature, they even have entropy, a measure of disorder that, in this case, scales with the black hole's surface area, not its volume. It's as if every bit of information swallowed by the black hole gets stamped onto its event horizon like a cosmic fingerprint, preserved in Planck-scale pixels far tinier than atoms. Hawking radiation, the ghostly glow that causes black holes to slowly evaporate, is where quantum gravity takes center stage. According to quantum theory, empty space isn't truly empty. It's a bubbling soup of virtual particles popping in and out of existence. At a black hole's edge, these fleeting particle pairs can get torn apart. One falls in while the other escapes, carrying away energy. Over eons, this process bleeds the black hole dry. But here's the catch. Hawking's math suggests the radiation is random, devoid of any information about what fell in. That contradicts quantum mechanics' sacred rule that information can never be lost. The paradox has haunted physicists for decades. If black holes erase information, our understanding of reality's bedrock is fundamentally flawed. This tension between gravity's relentless pull and quantum mechanics' ironclad rules is where the holographic principle emerges as a possible solution. Proposed by Gerard T. Hooft and Leonard Susskind, the idea suggests that all the information swallowed by a black hole isn't lost inside its depths, but is instead encoded on its two-dimensional surface like a cosmic DVD. Every star, planet, or hapless astronaut that crosses the event horizon leaves behind a scrambled but recoverable imprint in the horizon's quantum fluctuations. Zoom out, and this principle might apply to the entire universe. Our three-dimensional reality could be a projection of information stored on some distant, unseen boundary, with gravity acting as the glue that translates between dimensions. The implications are staggering. If black holes preserve information holographically, then spacetime itself might be a kind of illusion, a convenient construct that emerges from deeper, more fundamental quantum interactions. Experiments to test these ideas are still in their infancy, but tantalizing clues exist. Gravitational wave detectors like LIGO could someday spot faint echoes in black hole mergers' ripples that betray the presence of a quantum-structured horizon. Meanwhile, theorists scramble to reconcile holography with other quantum gravity frameworks, from string theory's AD/S/CFT correspondence to loop quantum gravity's spin networks. Whether the holographic principle ultimately holds or not, black hole thermodynamics has already rewritten the rules of the game. It's shown us that the universe's most destructive objects might also be its most eloquent teachers, whispering secrets about how information, gravity, and quantum mechanics intertwine. And if we're listening closely, their paradoxes could guide us to the theory of everything, a framework where spacetime isn't the stage but part of the performance. The holographic principle turns reality inside out, suggesting everything we experience in three dimensions might just be a shadow cast by information scribbled on a distant two-dimensional surface. Picture a credit card hologram, tilt it, and a flat sticker suddenly gains depth, fooling your eye into seeing three dimensions where only two exist. Now scale that up to cosmic proportions. What if the stars, galaxies, and even your morning coffee are just incredibly detailed projections from a flat, borderless canvas we can't see? This isn't science fiction. It's a serious hypothesis born from black hole physics, where the math insists that all the information swallowed by a black hole doesn't vanish into its core but gets encoded on its event horizon, pixel by pixel. String theory supercharges this idea. In the late 1990s, physicist Juan Maldacena discovered a concrete holographic link, a theoretical universe where gravity operates in a five-dimensional space, but its physics perfectly mirror a four-dimensional quantum field theory on the boundary. It's as if the cosmos has a hidden instruction manual: solve a simpler, gravity-free equation on the surface, and the answers automatically describe the warped, gravity-filled world within. This AD/S/CFT correspondence became a Rosetta Stone, revealing that spacetime itself might be emergent, like waves on an ocean whose true essence is the water's movement, not the shapes we see. But the real magic happens when you apply holography to black holes. When matter falls in, its information doesn't disappear. It's scrambled across the horizon's surface like a cosmic hard drive. Over time, that data can theoretically be decoded, meaning black holes aren't information shredders but the universe's most secure storage devices. Experiments are already hunting for hints of this principle. Some theories predict that if spacetime is holographic, gravitational waves from colliding black holes should carry faint echoes, subtle glitches in the ripple patterns that betray a pixelated underpinning. Other proposals suggest quantum entanglement, that spooky connection between particles, might be the glue holding the hologram together, with each entangled pair acting like a stitch between dimensions. Critics argue holography feels more like a mathematical trick than tangible physics after all. How do you prove our universe isn't real? Yet supporters counter that it elegantly solves quantum gravity's thorniest problems, from taming infinities to preserving information. Whether the holographic principle ultimately holds or not, it's reshaped how we see reality, suggesting that the solid, 3D world we navigate daily might just be the universe's most convincing illusion, a projection from a shadow dimension we've yet to find. Here's where the holographic principle gets its sharpest mathematical edge: the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. Picture a snow globe. Inside, you've got a tiny 3D world with gravity, physics, and maybe even tiny people building snowmen. But the entire scene is actually painted on the inside of the glass, a 2D surface that somehow contains all the information needed to recreate the 3D reality within. That's AD-S/CFT in a nutshell. It's a precise mathematical recipe showing how a universe with gravity in higher dimensions, like the snow globe's interior, can be perfectly described by a quantum field theory living on its boundary, the glass surface, no gravity required. The genius of this duality lies in its unexpected symmetry. In the higher dimensional bulk space, strings warp spacetime, black holes collapse, and cosmic dramas unfold. But on the lower dimensional boundary, there's no gravity, just particles interacting via quantum fields like characters in an elaborate computer simulation. Solve a problem on one side, and the answer translates flawlessly to the other. It's as if the universe handed physicists a decoder ring. Crack the quantum equations on the flat boundary, and the mysteries of curved spacetime in the bulk reveal themselves. Juan Maldacner's 1997 paper proposing this link didn't just bridge two theories. It suggested spacetime itself might be a secondary phenomenon, emerging from quantum entanglement like a 3D mirage rising from a 2D desert. What makes AD-S/CFT so revolutionary is how it demystifies black holes. Take a black hole in the bulk, a chaotic, inscrutable singularity. On the boundary, it becomes a hot, dense plasma of quantum particles, with entropy and temperature matching Hawking's predictions perfectly. Information isn't lost, it's scrambled into a quantum code on the surface. Even wormholes, those hypothetical shortcuts through spacetime, map to quantum entanglement on the boundary. Two particles entangled across light years, that's the holographic shadow of a wormhole threading the bulk. The implications are staggering. If spacetime is emergent, then distance and time might just be convenient illusions, ways our brains interpret deeper quantum relationships. Yet AD-S/CFT isn't a perfect mirror of our universe. The math works best for an anti-de Sitter space, a cosmos with negative curvature, unlike our own flat or positively curved reality. Critics argue it's like having a key that only fits a lock we've never seen. But supporters counter that the principle, not the specifics, matters. Just as Newton's idealized frictionless plane taught us about real motion, AD-S/CFT reveals universal truths about how spacetime and quantum information intertwine. Experiments may someday test its predictions, like quantum computers simulating boundary theories to see if gravitational effects emerge. Until then, this correspondence stands as a beacon, proof that even the most concrete aspects of reality, like space and time, might just be the universe's most convincing performance. Eric Verland's entropic gravity doesn't just tweak Einstein's equations, it flips them on their head, suggesting that what we call gravity might actually be the universe's way of balancing its books. But here's the twist: if gravity emerges from entropy, the relentless march toward disorder, then dark matter, the invisible glue holding galaxies together, might not be matter at all. Instead, Verland proposes it's an illusion, a side effect of how information on the cosmic horizon reshapes spacetime. Picture a crowded dance floor where the dancers don't realize their movements are being subtly guided by the room's acoustics. In this view, galaxies rotate faster at their edges not because of some unseen mass, but because space itself stores entropy gradients that mimic extra gravity. It's a bold claim, one that could erase dark matter from the cosmic ledger with a single mathematical stroke. The allure of entropic gravity lies in its economy. Dark matter has always been a cosmic placeholder, an invisible something we infer from its gravitational pull, yet never directly detect. Verland's framework offers an escape hatch. What if we're not missing particles but misreading spacetime's fine print? His equations reproduce galaxy rotation curves without invoking mysterious matter, and they even predict new relationships between a galaxy's mass and its entropy, predictions that, in some cases, align startlingly well with observations. For galaxies like NGC 1543, where dark matter models need careful tuning, entropic gravity slips into place like a key finding its lock. Yet critics aren't convinced. The biggest hurdle: galaxy clusters. These colossal structures, where hundreds of galaxies swirl in a gravitational embrace, exhibit behavior that's harder to explain without dark matter's extra pull. Entropic gravity struggles to account for the infamous bullet cluster, where colliding galaxies left behind gravitational fingerprints suggesting unseen mass trailing behind visible stars. Verland's defenders argue that his theory's full implications for large-scale structures are still unfolding, but skeptics counter that until it can match dark matter's success across all scales, it's more intriguing than definitive. Then there's the mathematical fine print. Entropic gravity borrows heavily from holography, treating spacetime as an information processing system. But some physicists argue Verland's entropy calculations rely on assumptions about quantum entanglement that remain unproven. Others point out that his theory doesn't yet mesh neatly with general relativity's triumphs, like the precise bending of light around stars or the timing of gravitational waves. Without these pieces, entropic gravity risks feeling like a beautiful idea that's not quite ready for prime time. But perhaps the theory's real value lies beyond proving or disproving dark matter. It forces us to ask, what if gravity isn't fundamental at all? Just as temperature emerged from the chaos of atoms, could spacetime's curvature be a collective effect of deeper information-theoretic rules? Whether Verland's vision ultimately holds or not, it's already stretched our imagination, revealing that the universe's mysteries might not lurk in the shadows of unseen matter, but in the holographic fine print of reality itself. Quantum gravity turns the universe into the ultimate social network, not of people, but of fundamental connections that rewrite space itself. Imagine waking up one day to discover that the empty void around you isn't empty at all, but a vast, dynamic web of relationships, like a cosmic game of connect the dots where every dot is a quantum event and every line is a flickering bond between them. At ultra-high energies, this web might be a chaotic tangle with no concept of distance or direction, a primordial soup of potential geometry. But as the universe cools, those connections snap into an orderly lattice, crystallizing into the structured spacetime we recognize. It's as if the early cosmos was a gas of abstract links, and the Big Bang was the moment it froze into a solid, giving rise to the familiar dimensions we move through today. The theory's name isn't just wordplay, it captures its core idea. Just as graphene's honeycomb lattice gives rise to extraordinary material properties, quantum gravity suggests that spacetime's properties, its theirness, emerge from an underlying graph of quantum interactions. Where general relativity treats spacetime as a smooth, continuous fabric, gravity argues it's more like a digital mesh, with each node representing a quantum degree of freedom. At tiny scales, this network might shimmer with defects, missing or strained connections that could manifest as dark energy, the mysterious force accelerating the universe's expansion. Picture stretching a spiderweb. Some threads slacken while others tauten, creating regions where the fabric of space itself resists or encourages stretching in ways that mimic an invisible energy field. What sets quantum gravity apart is its radical reimagining of dark energy. Instead of invoking some exotic fluid or cosmological constant, the theory proposes that dark energy could be a side effect of spacetime's incomplete freezing process. As the universe expanded, some quantum connections might have failed to fully stabilize, leaving a faint tension in the cosmic web like wrinkles in a half-smoothed bedsheet. These imperfections could generate repulsive gravity on cosmic scales, perfectly mimicking the effects of dark energy without requiring new particles or fields. It's a compelling twist. The very structure of space, not some hidden substance, might be pushing galaxies apart. Yet challenges remain. Critics point out that while quantum gravity elegantly describes how spacetime could emerge, it struggles to reproduce all of general relativity's precise predictions, like the exact bending of starlight around the sun. Others argue that testing the theory requires probing energies beyond anything achievable in particle colliders, but supporters counter that subtle signatures might lurk in the cosmic microwave background's faintest fluctuations, or in the way high-energy gamma rays travel across the universe, hints that spacetime has a graininess betraying its graph-like origin. Whether quantum gravity ultimately reshapes physics or not, it embodies a thrilling shift in perspective. It dares us to consider that space and time aren't foundational but secondary, an illusion woven from countless quantum handshakes. And if that's true, then every star, every planet, and even the emptiness between them is just a pattern in the universe's deepest, most intricate conversation. Group field theory walks a tightrope between two worlds, loops and fields, stitching them together with a mathematical fabric so elegant it might just reveal how space-time emerges from pure abstraction. Picture this: instead of points or strings, the universe's building blocks are abstract algebraic structures, like cosmic chords vibrating in a hidden mathematical space. These aren't physical objects but elements of symmetry, groups, the same kinds of patterns that describe how particles spin or how crystals repeat. Here's the twist: when these group elements intertwine, they don't just describe space-time, they create it, like a symphony whose notes conjure the very stage they're played on. At its heart, group field theory takes the core ideas of loop quantum gravity, the notion that space is woven from discrete loops, and grafts them onto the framework of quantum field theory, the language of particles and forces. But there's a radical shift. Instead of tracking loops in space, the theory treats space itself as a secondary effect, bubbling up from the interactions of these abstract group elements. Think of it like a murmuration of starlings. Individually, each bird follows simple rules, but together, their movements sculpt fleeting shapes in the sky. Similarly, group field theory suggests that the smooth geometry of space-time is a collective dance of countless quantum birds, each fluttering in an algebraic dimension we can't see. Where the theory gets explosive is in its approach to the Big Bang. Just as loop quantum gravity replaces the singularity with a bounce, group field theory envisions the birth of the universe as a phase transition, a moment when the chaotic interactions of group elements suddenly crystallized into the orderly space-time we know. It's as if the early cosmos was a boiling pot of mathematical possibilities, and the Big Bang was the instant the broth cooled into ice, locking in the structure of reality. Some models even suggest that remnants of this transition might linger in the cosmic microwave background, like faint cracks in the frozen surface of space-time. Critics, though, raise eyebrows at the theory's abstractness. Unlike strings or loops, group field theory's ingredients lie groups. Spin networks don't map easily to everyday intuition. Detractors argue it's like trying to explain music by discussing sound waves without ever mentioning instruments. And while the math produces tantalizing glimpses of emergent space-time, it hasn't yet reproduced all of general relativity's precise predictions, like the exact bending of light around stars. Yet the theory's defenders see its abstraction as a strength, not a weakness. By stripping space-time down to its algebraic bones, group field theory might uncover universal principles that other approaches miss, rules so fundamental they'd hold true in any possible universe, not just ours. Future supercomputers could simulate these group interactions at scales mimicking the early cosmos, hunting for signatures of space-time's emergence. And if the math holds, we might finally glimpse the answer to physics' deepest riddle, not just how gravity works, but why there's a where for it to work in at all. Whether group field theory ultimately unites loops and fields or not, it's already reshaped the quest for quantum gravity. It dares us to consider that space-time isn't the foundation of reality, but the finale of a hidden mathematical performance, one we're only beginning to decode. What if the deepest secret of space-time isn't about how it bends or stretches, but how it scales? Shape dynamics dares to rewrite Einstein's playbook by trading relativity's sacred space-time symmetry for something far stranger, conformal symmetry, the rule that physics should stay the same even if you zoom in or out like a cosmic camera lens. Forget bending light around stars. This theory suggests gravity might actually be the universe's way of balancing its scales, ensuring the laws of physics hold true no matter how you stretch or squash the cosmic backdrop. It's as if reality has a hidden preference for shape over size, with gravity acting as the referee that keeps everything in proportion. The magic lies in trading one symmetry for another. Einstein's general relativity treats space and time as fluid, dynamic entities warping together under gravity's influence. Shape dynamics disagrees. Instead of blending space and time into a single continuum, it treats space as fundamentally separate, with time emerging from how spatial geometry evolves. But here's the twist. While it ditches space-time's fusion, it demands conformal invariance, the idea that angles and proportions must stay consistent even if distances change. Picture inflating a balloon with dots on it. The dots might spread apart, but the angles between them remain the same. Shape dynamics argues the universe works similarly. Gravity isn't about warping space-time, but enforcing geometric relationships that transcend scale. Where this theory shines is in its radical simplicity. By decoupling space from time, it sidesteps some of quantum gravity's nastiest paradoxes, like the problematic blend of causality and quantum uncertainty. Black holes, for instance, transform from chaotic singularities into balanced geometric configurations, regions where conformal symmetry holds sway, smoothing out the infinities that plague other theories. Even the Big Bang gets a makeover. Instead of a fiery singularity, shape dynamics suggests a moment of infinite scaling, where the universe was all proportions and no size, like a fractal waiting to snap into focus. Yet for all its elegance, shape dynamics remains a quiet rebel in the quantum gravity arena. Critics argue that conformal symmetry struggles to explain why we experience time as a relentless, one-way flow, a cornerstone of physics that Einstein's relativity handles effortlessly. Others point out that the theory hasn't yet reproduced all of general relativity's triumphs, like the precise precession of Mercury's orbit or the exact delay of signals passing near the Sun. Without these validations, it's hard to dethrone space-time as the reigning framework. but its supporters counter that shape dynamics isn't meant to replace relativity, it's meant to reframe it. Just as quantum mechanics and Newtonian physics coexist at different scales, shape dynamics might reveal a hidden layer of geometric truth that only becomes vital at the Planck scale or in the heart of black holes. Future work could bridge the gaps, perhaps showing how conformal symmetry subtly warps into space-time under everyday conditions. Until then, shape dynamics stands as a provocative reminder. Sometimes the most revolutionary ideas aren't about adding complexity but stripping it away, revealing the universe's hidden sense of proportion. While most quantum gravity theories focus on warping space-time or adding hidden dimensions, causal fermion systems take a radically different tack. They rewrite the rules from the ground up using the universe's most stubborn particles, fermions. Picture reality not as a stage or a fabric, but as a vast dynamic sea of matter particles like electrons and quarks, each carrying just enough information to dictate how it interacts with its neighbors. These aren't passive dots floating in space, they're the architects of space itself, with every handshake between fermions subtly sculpting the geometry we experience as gravity. The theory's architect, physicist Felix Finster, saw fermions as more than building blocks, they're cosmic storytellers, encoding causality into their very existence. In this framework, every fermion's trajectory is a thread in a grand causal web, with the threads knotting and braiding to form what we perceive as space-time. Unlike string theories, vibrating filaments, or loop quantum gravity's woven loops, here the universe is a network of yes or no questions. Did particle A influence particle B? The answers don't just describe reality, they define it, with gravity emerging as a statistical tendency, the universe's way of averaging out trillions of these causal votes into smooth, Einstein-like curvature. Where the theory dazzles is in its austerity. It doesn't need extra dimensions or unseen particles, just fermions and their unwavering commitment to cause and effect. Even quantum fields, those ethereal entities that fill traditional physics, become secondary, mere bookkeeping tools for tracking fermionic relationships. Black holes, those notorious paradox factories, transform into dense knots of causal links, their event horizons marking the edge of where information can still flow freely. The Big Bang, a phase transition where fermions first locked into a stable causal dance, trading chaos for structured existence. Yet for all its elegance, causal fermion systems remain niche. Critics argue the math, while self-consistent, feels like a closed loop, a beautiful abstraction that hasn't yet produced testable predictions to rival general relativity's precision. Others point out that fermions alone seem ill-equipped to explain phenomena like dark energy or the universe's large-scale smoothness, but supporters counter that the theory is young, and its true power might lie in unexplored corners, like simulating fermionic networks on quantum computers to watch space-time emerge from raw causality. What makes this approach unforgettable isn't its popularity, but its audacity. It doesn't tweak Einstein's universe, it asks why we assumed space-time was fundamental in the first place. Whether it ultimately unites quantum mechanics and gravity or not, it's a masterclass in reimagining reality from the ground up, one fermion at a time. Massive gravity throws a wrench into Einstein's pristine vision by daring to ask, what if the graviton, the hypothetical particle carrying gravity's force, isn't massless after all? For decades, physicists assumed gravitons had to be weightless, just like photons, to perfectly match general relativity's predictions. But what if that assumption blinded us to a wilder possibility? Imagine gravity as a force that weakens not just with distance, but also over time, like a radio signal fading as it travels through fog. That's the heart of massive gravity. Gravitons with even a tiny mass could subtly alter how the universe expands, how galaxies cluster, even how black holes evaporate. The idea isn't new. In the 1930s, physicists Ernst Stueckelberg and Marcus Fiers toyed with giving gravitons mass, but their equations spat out a terrifying flaw: ghost modes. These weren't Casper the Friendly Ghost phantoms, but mathematical artifacts that threatened to destabilize reality itself. Negative probabilities, runaway energies, a cosmic house of cards waiting to collapse. For decades, this ghost problem made massive gravity seem like a dead end. Then, in 2010, a breakthrough. Claudia de Ram, Gregory Gabadads, and Andrew Tolley cracked the code, constructing a ghost-free version by layering gravitons with intricate self-interactions, like a set of Russian dolls where each layer corrects the last's instability. Their theory, dubbed DRGT massive gravity, became the first credible challenger to Einstein's massless regime. Where massive gravity gets thrilling is in its cosmic consequences. If gravitons have mass, gravity might weaken over vast distances, an effect that could explain dark energy without invoking mysterious fields. Picture a universe where gravity's reach isn't infinite but fades beyond galactic scales, letting expansion accelerate naturally. Even black holes could morph under this regime, with their event horizons fraying like worn fabric as massive gravitons leak energy into the void. Some models suggest these black holes would leave behind echoes in gravitational wave detectors, subtle ripples betraying their modified gravity. Yet the theory isn't without skeptics. Critics argue that while DRGT solves the ghost problem mathematically, it feels contrived, like balancing a pencil on its tip for eternity. Others point to tensions with precision tests of general relativity, like the laser-ranging experiments that confirm Einstein's predictions to razor-thin margins. But supporters counter that massive gravity's deviations might only appear in extreme environments, near black holes in the early universe or across cosmic voids where gravity's grip is weakest. Whether massive gravity ultimately unseats Einstein or not, its audacity is undeniable. It forces us to confront a radical notion that gravity, the force that sculpts galaxies, might be fundamentally incomplete, a cosmic fugitive still hiding its full nature in plain sight. And if even one of its predictions holds up, the universe just got a whole lot stranger. Bimetric gravity flips the script on Einstein's universe by proposing a cosmic duet, not one, but two space-time metrics interacting in an intricate dance. Picture two overlapping grids, one governing the geometry we experience with stars, planets, and light bending predictably, while the other lurks in the background, invisible yet influential, tugging at the fabric of reality in ways we've mistaken for dark energy. This isn't just doubling down on dimensions, it's reimagining gravity as a conversation between two entirely different rulebooks for space and time, each with its own curvature, its own rhythm. The theory's elegance lies in its economy. Instead of inventing exotic particles or hidden fields to explain the universe's accelerating expansion, bimetric gravity suggests the answer might be hiding in plain sight, a second metric stretching space-time from behind the scenes. Think of it like a puppeteer working two sets of strings. Our observable universe responds to one set, while the other silently adjusts the tension, creating the illusion of an unseen force pushing galaxies apart. The math reveals something profound. When these metrics interact, their interplay can mimic dark energy's repulsive effect without requiring a cosmological constant or quintessence. Where bimetric gravity gets provocative is in its testable predictions. Unlike some quantum gravity models that retreat into untestable abstraction, this framework leaves fingerprints. If a second metric exists, it could subtly alter how gravitational waves propagate, leaving faint echoes in detectors like LIGO. The cosmic microwave background might bear scars of this duality, with anomalies in its polarization patterns hinting at a hidden gravitational counterpart. Even black holes could behave differently. Their event horizons might shimmer with interference patterns, like ripples from a stone tossed into a pond with two competing surfaces. Yet the theory isn't without friction. critics argue that introducing a second metric feels ad hoc, a clever workaround rather than a fundamental solution. Others point to fine-tuning challenges. The two metrics must interact just precisely enough to mimic observed cosmic acceleration without destabilizing the solar system's delicate gravitational choreography. But supporters counter that all groundbreaking theories face skepticism before validation. After all, Einstein's relativity once seemed excessive too, until eclipses and atomic clocks proved otherwise. What makes bimetric gravity so compelling is its refusal to accept dark energy as a given. It dares to ask, what if the universe's expansion isn't driven by some mysterious energy, but by the hidden interplay of two spacetimes, one we see and one we've yet to fully glimpse? Whether it ultimately revolutionizes physics or becomes a stepping stone, it reminds us that sometimes the most profound answers lie not in adding layers to reality, but in questioning how many layers we've missed. Rainbow gravity turns the universe into a cosmic kaleidoscope where space-time isn't just curved, but color-coded by energy. Imagine a prism that doesn't just bend light, but warps reality itself. High-energy particles like gamma rays could experience space-time as a steeper hill than low-energy photons, causing them to lag behind like sprinters fighting thicker air. This isn't science fiction, it's a radical reimagining of Einstein's relativity, where the fabric of the universe becomes energy-sensitive, stretching and compressing based on what's passing through it. The theory's name isn't just poetic, it reflects a profound shift. Just as a rainbow separates sunlight into bands of color, rainbow gravity suggests space-time might sort particles by their energy, altering how they perceive distance and time. The implications ripple across the cosmos. If space-time reacts differently to different energies, then a gamma-ray burst, a violent explosion billions of light-years away, could arrive at Earth with its highest energy photons slightly delayed, like the last notes of a cosmic symphony trailing behind the crescendo. Astronomers have already scoured data from observatories like the Fermi Gamma-Ray Space Telescope for these telltale lags. In 2019, a gamma-ray burst catalogued as JB 190829 seemed to show hints of this energy-dependent delay, sparking fevered debate. Was it a fluke, dust interference, or the first whisper of rainbow gravity's prism effect? Follow-up studies remain inconclusive, but the hunt is far from over. Critics argue the theory faces an uphill battle. For rainbow gravity to match observations, its energy-dependent effects must be exquisitely fine-tuned, strong enough to show up in gamma-ray data, yet weak enough to avoid contradicting decades of precision tests in particle physics. Others point out that alternative explanations, like quantum foam models or interstellar medium effects, could mimic the same delays without rewriting relativity. But supporters counter that rainbow gravity's elegance lies in its testability. Unlike some quantum gravity theories that retreat into mathematical abstraction, this one leaves fingerprints we can chase, whether in gamma-ray bursts, ultra-high-energy cosmic rays, or even subtle anomalies in the way gravitational waves from colliding neutron stars disperse across frequencies. What makes rainbow gravity so captivating isn't just its potential to unify quantum mechanics and gravity. It's the audacity to suggest that space-time isn't a static stage, but a dynamic filter, subtly tinting the universe's behavior based on who's looking and how hard. Whether the theory ultimately shines or fades, it's already reshaped how we see the cosmos, not as a monochrome expanse, but as a spectrum of possibilities, waiting to be decoded one photon at a time. Quantum Einstein gravity takes a refreshingly back-to-basics approach in the quest to unify quantum mechanics and general relativity. No extra dimensions, no hidden universes, just a stubborn insistence that gravity should behave like every other quantum field. Picture this: electromagnetism has the photon, the strong force has gluons, so why shouldn't gravity have its own quantum particle, the graviton, playing by the same rules? That's the heart of this framework, treating gravity not as geometry, but as a force mediated by particles, then using the same mathematical toolkit that worked for every other fundamental interaction. The magic here lies in a technique called asymptotic safety, a fancy term for gravity's potential to become predictable at incredibly high energies, like a stormy sea calming into glass as you zoom in. In traditional quantum field theory, calculations often spiral into infinities when you probe tiny scales, but certain forces, like electromagnetism, have a built-in safety net called renormalizability that keeps the math sane. Gravity, famously, doesn't play nice until quantum Einstein gravity suggests it might. Imagine gravity's strength isn't fixed but adjusts with energy like a thermostat, dialing itself down at extreme scales to avoid mathematical chaos. If true, this would mean Einstein's equations aren't broken. They just have a hidden clause we've missed, one that lets quantum gravity emerge naturally without reinventing spacetime. Where this theory shines is in its concrete predictions. Unlike some quantum gravity models that float in abstract math, quantum Einstein gravity leaves footprints we might actually detect. For instance, it suggests subtle changes in how gravity behaves at ultra-short distances, perhaps altering the way black holes evaporate or leaving faint wrinkles in the fabric of spacetime that future gravitational wave detectors could spot. Some versions even propose that the universe's expansion might accelerate differently at quantum scales, offering an alternative explanation for dark energy without invoking mysterious substances. Yet gaps remain. Critics argue that proving asymptotic safety requires solving equations of mind-bending complexity, so tough they make string theory look like algebra. Others point out that while the framework tames gravity's quantum quirks, it hasn't yet reproduced all of general relativity's triumphs with equal precision, like the exact bending of starlight around the sun. And then there's the elephant in the room. Without extra dimensions or radical new physics, can this approach truly capture gravity's uniqueness, or is it forcing a square peg into a round hole? What makes quantum Einstein gravity so compelling, though, is its sheer stubbornness. It doesn't demand we accept unseen dimensions or holographic universes, just that we reconsider gravity's quantum resilience. Whether it ultimately succeeds or not, it stands as a reminder that sometimes the most revolutionary ideas aren't the flashiest, just the ones that force us to read the fine print on reality's oldest equations. Wormholes aren't just science fiction. They might be hiding in plain sight, woven into the quantum fabric of reality itself. Picture a cosmic shortcut, a tunnel stitching together two distant points in space-time like a hidden thread pulled taut through the universe. In Einstein's general relativity, these structures are called Einstein-Rosen bridges, mathematical curiosities that collapse faster than they form, crushed by the very gravity they rely on. But quantum gravity flips the script. What if the key to stable wormholes lies not in cosmic engineering, but in the spooky connections of quantum entanglement? Enter the AR equals EPR conjecture, a bombshell idea that ties wormholes directly to the quantum phenomenon Albert Einstein famously dismissed as spooky action at a distance. Here's the radical premise: when two particles become entangled, their fates linked no matter how far apart they drift. They might be connected by a microscopic wormhole, a Planck-scale tunnel too tiny to traverse but fundamental to the universe's architecture. It's as if quantum entanglement doesn't just defy space-time, it redefines it, stitching the cosmos together with invisible bridges we're only beginning to map. The implications are staggering. If entanglement and wormholes are two sides of the same coin, then black holes, already notorious for stretching space-time to its limits, could be gateways in disguise. Imagine two black holes entangled at birth, their fiery cores linked by a wormhole even as they drift billions of light-years apart. Throw something into one, and information might not vanish into a singularity but emerge from the other, scrambled but preserved. This isn't just theoretical sleight of hand. It's a potential solution to the black hole information paradox. the puzzle of whether data swallowed by black holes is truly lost or merely hidden in quantum knots. But how could something as delicate as entanglement, which links fragile particles, sustain a wormhole against gravity's crushing grip? The answer might lie in quantum gravity's weirdest quirk, negative energy. In theory, a wormhole's throat could be propped open by exotic matter, a substance with negative mass that repels rather than attracts. While this sounds like fantasy, quantum fields already produce fleeting bursts of negative energy in the form of Casimir effects, where empty space itself pushes microscopic plates together. Scale this up and you've got a recipe for a traversable wormhole, a tunnel where the repulsive force counteracts gravity's pull, at least for an instant. Critics argue that ER equals EPR remains speculative, a beautiful metaphor without experimental teeth. After all, how do you probe a Planck-sized wormhole lurking inside a pair of entangled particles? Yet supporters point to quantum computers as potential testing grounds. By mimicking entangled black holes in controlled circuits, researchers might spot signatures of wormhole dynamics, like information reappearing in unexpected ways or correlations that defy classical explanations. Already, experiments with holographic quantum systems have teased hints of wormhole-like behavior, though the debate rages over whether these analogies hold in real space-time. Whether wormholes are the hidden scaffolding of entanglement or just a provocative analogy, the ER equals EPR conjecture has already reshaped the quantum gravity landscape. It blurs the line between information and geometry, suggesting the universe's deepest connections aren't forged in space, but through it, like a secret network of tunnels too small to see but too profound to ignore. And if that's true, then every entangled particle, every black hole, and maybe even you are part of a vast, invisible labyrinth, stitching the cosmos together one quantum thread at a time. Simplicial quantum gravity takes the chaos of spacetime and slices it into orderly geometric chunks, like dissecting the universe with a cosmic scalpel. At its core are simplices, the building blocks of this theory, triangles in 2 dimensions, tetrahedrons in 3, and their higher dimensional cousins forming the scaffolding of reality itself. Picture spacetime not as a smooth, flowing fabric, but as a vast dynamic mosaic where each tiny tile is a simplex, snapping together to approximate curvature through sheer brute force geometry. It's a bit like pixelating a photograph. Up close, you see jagged edges, but step back and the image resolves into seamless curves. What sets this approach apart is its ruthless practicality. While other quantum gravity theories wrestle with abstract math or unproven symmetries, simplicial quantum gravity rolls up its sleeves and computes. By gluing these simplices edge to edge in simulations, physicists can numerically explore how spacetime behaves at the Planck scale, where quantum fluctuations rip apart smooth geometry into a frothy, ever-changing foam. The equations of general relativity don't get rewritten here. They get discretized, broken into finite steps a supercomputer can crunch. Imagine rebuilding Einstein's universe from Lego bricks, then shaking the table to see how the structure holds up under quantum turbulence. The magic happens in the simulations themselves, using techniques like reg calculus, a method to approximate curvature by tweaking the angles between simplices. Researchers can model everything from black hole mergers to the Big Bang's fiery dawn. One striking result: the universe might naturally avoid singularities, with simplices resisting infinite collapse like a microscopic safety net. In some simulations, spacetime even undergoes spontaneous phase transitions, flipping from a chaotic quantum soup into the orderly geometry we recognize, a digital echo of cosmic inflation. Yet the theory isn't without skeptics. Some argue that simplicial approximations introduce artificial, lattice artifacts, glitches in the simulation that don't reflect true physics. Others question whether this computational brute force can ever capture the elegance of analytic solutions. But supporters counter that sometimes you need to get your hands dirty to uncover truths pure math might miss. And as supercomputers grow more powerful, these digital universes could reveal patterns no equation ever predicted, hinting at spacetime's true nature, one simplex at a time. Teleparallel gravity rewrites Einstein's cosmic playbook by flipping the script on how we think about gravity's geometry. While general relativity paints gravity as the curvature of spacetime, like a bowling ball sinking into a trampoline, this theory swaps curvature for torsion, a twisting force that gives spacetime a subtle, screw-like structure. Imagine spacetime not as a stretchy fabric, but as a vast network of rigid scaffolding, where gravity emerges from how each beam twists against its neighbors. It's a radical shift. Instead of planets rolling along warped curves, they're guided by invisible spirals in the cosmic framework, like marbles following the grooves of a spiral slide. At the heart of teleparallel gravity lies the Weizenberg connection, a mathematical tool that replaces Einstein's curvature-centric equations with one's tracking torsion. The surprising part, at the cosmic scale, both frameworks predict identical outcomes: planets orbit stars, light bends around galaxies, meaning teleparallel gravity isn't wrong, just different under the hood. But dive into the quantum realm and the theories diverge sharply. Curvature-based gravity struggles with infinities at tiny scales, but torsion might offer a backdoor. Picture spacetime's twisting structure acting like a built-in regulator, suppressing quantum fluctuations before they explode into nonsense. Some models even suggest that teleparallel gravity's equations avoid the notorious non-renormalizability that plagues Einstein's approach, hinting at a smoother path to quantum compatibility. Quantum extensions of teleparallel gravity take this further, proposing that torsion could be the missing link between gravity and the standard model. If spacetime's twists interact with quantum fields, they might generate particle masses or even explain dark matter as a side effect of torsion's invisible torque. One provocative idea suggests that the Higgs boson, the particle responsible for mass, might not be fundamental, but an emergent property of spacetime's twisted geometry. It's as if the universe's building blocks aren't just in space, they're woven from it, with torsion threading the needle between the large and the small. Yet challenges remain. Critics argue teleparallel gravity's quantum versions often rely on speculative couplings between torsion and matter, lacking the clean symmetry of string theory or loop quantum gravity. Others point out that torsion's effects, if they exist, are so subtle we've yet to spot them in particle colliders or gravitational wave data. But supporters counter that the theory's experimental footprint might lie in extreme environments: neutron star collisions, the early universe's torsion-rich plasma, or even anomalies in quantum entanglement experiments. Whether teleparallel gravity ultimately unseats Einstein's framework or not, its bold reimagining of spacetime's geometry has already expanded the toolkit for quantum gravity. It reminds us that sometimes the most profound breakthroughs come not from adding layers to reality, but from twisting the lens through which we see it. Unimodular gravity dares to ask a seemingly simple question: what if the universe isn't as rigidly balanced as Einstein thought? In general relativity, the equations governing gravity are built on a foundation of strict mathematical symmetry, every term carefully tuned to preserve something called general covariance, which ensures the laws of physics hold no matter how you slice space and time. But unimodular gravity calls that into question by relaxing one of those constraints. Instead of treating space-time as an infinitely stretchable fabric, it suggests the cosmos might have a fixed volume element, like a canvas that can warp and bend but never expand or shrink overall. This subtle tweak doesn't just streamline the math, it could be the key to sidestepping some of quantum gravity's nastiest paradoxes. At its core, the theory trades Einstein's full suite of equations for a pared-down version where the determinant of the metric, the mathematical object encoding space-time's shape, is held constant. Think of it like switching from modeling the ocean's waves to focusing only on how water sloshes inside a sealed, unexpandable tank, the astonishing part. On cosmic scales, unimodular gravity reproduces nearly all of general relativity's predictions, from bending starlight to the expansion of the universe. But under the hood, something profound changes. The cosmological constant, that enigmatic force driving cosmic acceleration, stops being a fixed parameter and instead emerges as an integration constant, a number set by the universe's initial conditions, not baked into the laws themselves. This shift has tantalizing consequences for quantum gravity. One of the field's biggest headaches is the cosmological constant problem, the staggering mismatch between the predicted vacuum energy of quantum fields and the observed value of dark energy. Unimodular gravity softens this blow by decoupling vacuum energy from gravity's equations, effectively rendering it irrelevant to cosmic expansion. It's as if the universe has a built-in filter, ignoring the chaotic quantum noise and focusing only on the geometric twists that matter. Some physicists, like Nobel laureate Steven Weinberg, have even speculated that this could explain why the cosmological constant is so eerily small, a fluke of how our particular universe's initial volume element was set rather than a fine-tuned mystery. Yet for all its elegance, unimodular gravity remains a niche pursuit. Critics argue that while it simplifies certain problems, it introduces new ones, like how to reconcile its fixed volume with quantum fluctuations that should, in principle, distort space-time at the smallest scales. Others point out that the theory doesn't fully resolve quantum gravity's core challenges, such as renormalizability or the black hole information paradox. And then there's the aesthetic objection. To many physicists, tinkering with Einstein's symmetrical foundations feels like vandalizing a masterpiece, even if it makes the plumbing work better. Still, the theory's modest following includes stubborn optimists who see it as a road less traveled, one that might bypass the quagmire of competing quantum gravity frameworks. If space-time's volume truly is immutable, then perhaps the universe's deepest secrets aren't hidden in extra dimensions or holographic codes, but in the subtle art of what isn't allowed to change. Whether unimodular gravity ultimately rises to prominence or fades into obscurity, it stands as a reminder that sometimes progress in physics doesn't come from adding complexity, but from daring to subtract. Fractal space-time turns the universe into an infinite hall of mirrors where every zoom inward reveals new layers of structure, repeating in self-similar patterns down to the smallest scales. Imagine coastlines that never smooth out, no matter how close you look, or snowflakes where every tiny branch holds smaller copies of itself. Now apply that to the fabric of reality. What if space-time isn't smooth or pixelated, but endlessly intricate, with gravity and quantum mechanics blending seamlessly because they're part of the same geometric tapestry? This wild idea, championed by physicists like Laurent Notel, suggests that the infinities plaguing quantum gravity calculations might vanish if we stop assuming space-time is flat and featureless at tiny scales. Instead, it could twist and fold at every level, like a cosmic fractal where even the tiniest crinkle has its own microscopic landscape. The magic lies in how fractals handle extremes. In traditional physics, trying to calculate what happens at a point like singularity, like the center of a black hole, makes equations explode into nonsense. But fractal geometry thrives at boundaries. Picture zooming into the jagged edge of a Koch snowflake. No matter how deep you go, the length stays finite because the complexity grows in perfect balance with the scale. Apply that to space-time, and singularities transform from mathematical monstrosities into natural features of the fractal terrain. Even quantum fluctuations, which normally threaten to rip space apart, could become orderly vibrations riding the fractal waves, like ripples cascading down a never-ending staircase. Where fractal space-time gets controversial is in its testable predictions. If the universe has a fractal structure at quantum scales, high-energy particles traveling through it should exhibit subtle anomalies like tiny deviations in their speed or spin that betray the hidden texture beneath smooth space. Some experiments have claimed to spot these fingerprints. In 2011, the Opera collaboration made headlines when they reported neutrinos apparently moving faster than light, a result later traced to faulty wiring, but fractal theorists wondered if it might have been a fleeting glimpse of space-time's underlying graininess. More recently, quantum optics experiments studying photon propagation through engineered fractal materials have shown light behaving in ways that classical space can't explain, hinting that fractal physics might play well with quantum rules after all. Critics argue that fractal space-time is more poetry than physics, a beautiful metaphor lacking rigorous mathematical scaffolding. Without a clear mechanism for how classical smoothness emerges from quantum fractalness, the theory risks being untestable. Others point out that fractal geometry alone doesn't solve gravity's non-renormalizability. It just kicks the can down an infinitely recursive road. But supporters counter that every radical theory starts half-baked from quarks to black holes. The real test will come when quantum gravity experiments like precision measurements of atomic spectra or gravitational wave echoes either find fractal signatures or rule them out conclusively. Until then, fractal space-time remains a tantalizing what-if, reminding us that sometimes the universe's deepest answers aren't found in simplicity, but in infinite complexity. Quantum causal histories turn the universe into a cosmic story book where every event is a sentence, and the accumulation of sentences builds the very fabric of reality. Unlike theories that treat space-time as a static stage, this framework suggests reality unfolds like a narrative, with each quantum event stitching itself into the growing tapestry of cause and effect. Picture a grand domino rally, but instead of dominoes, you have flickering moments of possibility, each one influenced by what came before and shaping what comes next. The twist space-time isn't the backdrop for these events. It's the result of them, emerging from their interconnections like a sculpture carved from relationships rather than marble. At the heart of this idea is a radical shift in perspective. Instead of asking how particles move through space and time, quantum causal histories ask how particles create space and time through their interactions. Think of it like a social network. Each post, like, or comment is an event, and the sprawling web of connections is the platform itself. In this universe, a photon's journey from a star to your eye isn't just a path through pre-existing space, it's one thread in a dynamic weave that defines distance and duration as it unfolds. Mathematically, this translates to a partial order of events, a timeline where some events must precede others, like your coffee cooling before you drink it, while others remain unlinked, floating in quantum ambiguity until an interaction locks them into the causal flow. Where this theory collides with quantum computing is nothing short of mind-bending. Quantum computers thrive on superposition, the ability to explore multiple paths simultaneously, and quantum causal histories suggest reality might work the same way. Before a measurement collapses a quantum system, countless potential histories coexist, each a tentative draft of space-time's story. This mirrors how quantum processors evaluate countless solutions at once, with the act of reading the output akin to the universe, choosing a single causal history from the quantum fog. Researchers are already borrowing techniques from quantum algorithms to simulate these histories, probing how space-time might emerge from quantum circuits programmed with causal rules. But the real magic happens when you link this to causal set theory, another approach that reduces reality to a network of cause and effect relationships. While causal sets focus on the structure of these connections, quantum causal histories inject dynamics like comparing a static family tree to a living, breathing saga where new branches grow with every decision. Together, they hint at a universe where the past isn't fixed but flexible, subtly reshaped by future events in a feedback loop that defies classical intuition. Imagine tossing a pebble into a pond, only to realize the ripples upstream are adjusting the moment the pebble left your hand, a cosmic version of reverse causality that quantum math might one day describe. Critics argue these ideas flirt with philosophy more than physics, lacking the concrete predictions that would make them testable. Yet supporters point to nascent experiments like quantum simulations of causal networks that could soon reveal whether space-time truly emerges from quantum storytelling. Whether quantum causal histories rewrite physics or fade into the archives, they've already gifted us a profound metaphor. That reality might not be a clockwork mechanism, but an epic in progress, one where every quantum event is a word and gravity perhaps just the grammar holding it all together. Spin foam models take the radical ideas of loop quantum gravity and breathe movement into them, transforming the static spin networks of space into a dynamic, frothy dance of quantum geometry. Imagine those spin networks we described earlier, the intricate webs of woven loops that define space at the smallest scales, but now picture them not as frozen snapshots, but as frames in a cosmic flipbook. Each frame represents a quantum leap in the structure of space-time, where loops interact, merge, or split, creating a foamy, ever-shifting landscape. This is the essence of spin foam, a history of space-time's evolution written in the language of quantum geometry, where every bubble and bridge in the foam corresponds to a possible way the universe can rearrange itself at the Planck scale. At the heart of this theory lies a deceptively simple question. What if space-time isn't just granular but animated? In loop quantum gravity, spin networks describe space's structure at a single moment, like a single still from a movie. Spin foam models stitch those stills together into a film, showing how space-time changes over time in discrete, quantum-sized steps. The foam in the name isn't just poetic. It reflects the theory's prediction that at microscopic scales, space-time resembles a seething mass of bubbles, each representing a quantum event where space's geometry shifts. These aren't literal bubbles, of course, but abstract mathematical structures where the loops of spin networks interact, creating a tapestry of possible transitions between states. One of the most striking aspects of spin foam models is how they handle the concept of time. In general relativity, time is smooth and continuous, flowing like a river. But in the spin foam framework, time becomes granular, advancing in tiny, irreducible jumps like a clock whose ticks are the indivisible moments when space-time's geometry updates. This solves a thorny problem in quantum gravity: how to blend the smooth, deterministic flow of Einstein's time with the probabilistic, jumpy nature of quantum mechanics. Spin foam sidesteps the paradox by suggesting that time is those jumps, with the foam's structure encoding all possible paths space-time could take, weighted by probability. Where spin foam models truly shine is in their approach to black holes and the Big Bang. Just as loop quantum gravity replaces the singularity with a bounce, spin foam offers a quantum history of how such a bounce might unfold. Picture a black hole's collapse not as a plunge into infinite density, but as a cascade of spin foam bubbles, each transition reconfiguring space-time until the collapse reverses into an expansion. Similarly, the Big Bang transforms from a single, inexplicable moment into a sequence of quantum geometric steps, a cosmic origami folding and refolding itself into existence. Some calculations even suggest that spin foam could naturally explain the universe's uniformity, with the foam's probabilistic, averaging, smoothing out wrinkles in early space-time, much like shaking a snow globe settles the flakes. Yet for all their elegance, spin foam models face formidable challenges. The math is notoriously complex, requiring advanced tools from quantum field theory and combinatorics. Critics argue that while the framework beautifully describes space-time's quantum evolution, it hasn't yet fully reproduced general relativity's predictions at large scales, like the precise orbit of Mercury or the bending of light around stars. Others point out that the theory's reliance on discrete steps makes it hard to reconcile with the apparent smoothness of the cosmos we observe. But supporters counter that spin foam is still in its adolescence, with breakthroughs emerging regularly. New computational techniques like tensor networks and quantum simulations are starting to bridge the gap between the foam's tiny quantum steps and the smooth spacetime we experience. And if the theory holds, it could unlock answers to some of physics' deepest mysteries, from the nature of dark energy to the fate of information in black holes. What makes spin foam models so captivating isn't just their potential to unify quantum mechanics and gravity. It's the audacious vision they offer, a universe where space-time isn't a static stage, but a living, evolving thing, a quantum foam bubbling with possibilities, each bubble a flicker in the grand story of reality. And if that's true, then every star, every galaxy, and even the void between them is just a pattern in the foam's endless dance. What if time, the steady, unyielding river we build our lives around, isn't fundamental at all, but a cosmic illusion? This is the chilling possibility at the heart of quantum gravity's problem of time, where the closer we scrutinize the universe's fabric, the more time seems to dissolve into mathematical smoke. In Einstein's general relativity, time is woven into the very structure of space-time, bending with gravity like a flexible fourth dimension. But when quantum mechanics enters the picture, time stops behaving. It becomes a stubborn variable that refuses to play by quantum rules, vanishing entirely in some equations like a magician's trick gone wrong. The conflict isn't just technical, it strikes at the core of reality. If time isn't foundational, why do we experience it so viscerally? And how do the competing theories of quantum gravity attempt to resurrect it from oblivion? Loop quantum gravity takes a pragmatic approach. It doesn't discard time but breaks it into discrete chunks. Picture a stop-motion animation where each frame represents a quantum of time, too small to perceive individually but strung together to create the illusion of flow. Here, time isn't continuous but granular, emerging from the interactions of spin networks, those intricate loops of quantum geometry we explored earlier. The catch: there's no master clock ticking in the background. Time becomes relational, defined purely by how one quantum event follows another, like dominoes in the dark. This internal time framework, championed by Carlo Rovelli, suggests our experience of duration might be nothing more than the universe comparing one state to another, with no absolute now to anchor it. String theory, meanwhile, sidesteps the problem by burying time in higher dimensions. In the holographic AD/CFT correspondence, time on the boundary of the universe where gravity vanishes maps mysteriously to time in the bulk where gravity reigns. It's as if time isn't native to our 4D world but borrowed from a shadow reality, like a projection flickering on a cosmic screen. Some versions even suggest time could emerge from entanglement particles synchronizing their quantum states across space, creating the illusion of a shared temporal flow. But critics argue this is sleight of hand, trading one mystery for another. The most radical stance comes from canonical quantum gravity, where the Wheeler-DeWitt equation famously erases time altogether. This equation, sometimes called the wave function of the universe, describes reality as a static block where past, present, and future coexist frozen, like frames in an unplayed film reel. Time's passage, in this view, is a psychological artifact, a trick of consciousness stitching together moments from a timeless whole. It's a haunting idea. The universe might not have a timeline, just an infinite gallery of nows we're sequentially walking through. Yet every theory faces the same existential hurdle. If time isn't fundamental, why does it feel so inescapably real? Some propose it's a thermodynamic illusion, emerging from entropy's relentless increase like a river flowing downhill. Others, like Julian Barber, argue time is a persistent mistake ingrained in our perception, a vestige of classical physics due for a quantum overhaul. Even the act of measurement in quantum mechanics, where observation collapses probabilities into definite outcomes, might be stitching time's illusion into reality, one decision at a time. What makes the problem of time so profound isn't just the technical puzzle, but what it reveals about our place in the cosmos. If time is emergent, then our most intimate experience, the feeling of moments slipping past, is a cosmic magic trick, a story the universe tells itself to make sense of its own equations. Whether time is reborn as a quantum artifact, a holographic shadow, or a thermodynamic mirage, one thing is clear. The deeper we dig into gravity's quantum heart, the less time looks like a river, and more like a hall of mirrors reflecting questions far stranger than the answers we found. From loops stitching space together to strings humming in hidden dimensions, we've journeyed through a labyrinth of cosmic ideas, each one bolder, stranger, and more beautiful than the last. Quantum gravity isn't just a single puzzle. It's a kaleidoscope of possibilities where every twist reveals a new way to reimagine the fabric of reality itself. Some theories whisper of universes bouncing back from collapse, while others paint space-time as a hologram or a cosmic network of cause and effect. And here's the thrilling part: none of these ideas are just wild guesses. They're rigorous, mathematically daring attempts to solve the deepest mystery in physics: how the universe's tiniest pieces dance with the force that shapes galaxies. What's astonishing isn't just the diversity of these theories, but how they reflect the audacity of human curiosity. Whether it's spin foam's quantum bubbles or Verlin's entropic gravity, each framework is a testament to our refusal to accept "we don't know" as a final answer. Even the disagreements, string theory's extra dimensions vs. loop quantum gravity's granular space, emergent gravity vs. dark matter's shadow, aren't setbacks. They're signposts pointing us toward gaps in our understanding that might hide the next Einstein-level breakthrough. So which theory resonates with you? The elegant minimalism of causal sets, where reality is just a web of before and after, or the symphonic beauty of string theory, with its vibrating notes composing the cosmos? Maybe you're drawn to the radical humility of asymptotic safety, where gravity might not need a revolution, just a clever rewrite of its fine print. There are no wrong answers here, only frontiers waiting to be explored. The quest for quantum gravity isn't just about equations, it's about rewriting the story of existence. And while we don't have all the pieces yet, every theory, every calculation, every what if brings us closer to glimpsing the universe's blueprint. So keep wondering, keep questioning, and remember, the greatest discoveries often begin as ideas too strange to believe. If you're as captivated by these cosmic riddles as we are, hit subscribe, because the next chapter in this adventure is being written right now, and you won't want to miss it. Until then, stay curious. The universe always has one more secret to share.